So today we're going to see a different way to do things. If you remember from physics class, you could always analyze a system using forces, which is what we have been doing up to now. But you can also analyze systems using energy. This is what we will be doing today. Specifically, today we will see the principle of virtual work. As you may remember, a force that causes a displacement does work, which is equivalent to F dotted with dr, or the force times the distance moved. Remember, it is only the displacement in the same direction as the force that counts, and hence the dot product. Equivalently, the work can be evaluated using the force times the displacement times the cosine of the angle between them. Work, being a form of energy, is measured in joules in the SI system or pounds-feet in the US system. Forces are not the only thing that can do work. Moments can also do work. Similar to forces, the work done by a moment is the magnitude of the moment times the displacement caused. In this case, angular displacement, d theta. Note that this must be measured in radians. If the moment and angular displacement are in the same direction, the work done is positive. Similar to the linear version, when the force and displacement are in the same direction, the work is positive. Now, the problem for this class is that we are dealing with statics. Therefore, there should be no motion. That is why this is called the principle of virtual work. We only imagine that a displacement can occur, giving rise to an equivalent amount of work called virtual work. To depict this imaginary displacement, they are usually denoted by little delta, as opposed to big delta or g, indicating that this displacement is only virtual. Then the virtual work is given by delta u equals F delta r cosine theta, or delta u equals m delta theta if we're dealing with rotation. Again, the delta u indicating that this work is virtual. So that is how the virtual work can be calculated. The principle of virtual work states that if a body is in equilibrium, then its virtual work must be zero, when taking into account all forces and moments acting on the body. This is equivalent to the body not wanting to move based on the current arrangement of forces and moments, which is the definition of equilibrium. So this is another way to determine the equilibrium state of objects instead of using Newton's second law and forces. Either method, Newton's second law or virtual work, can be used to solve any statics problem. In some cases, forces are easier. In some cases, work is easier. The cases where work is easier usually involve bodies with several connected members, such as the one shown below. And some of the ones on day 16, remember some of these ended up with 6 or 7 or even 8 unknowns. In these cases, the goal is to determine the position of each member as a function of a single variable, like x or y, or usually it ends up being in terms of some angle theta, as seen down here. As this is a new concept, seeing some examples will probably be most beneficial, but sticking to the theme of these videos, here is a pre-lecture example for you to try out. Obviously, this would be a very simple example if you were to use Newton's second law, rigid body equilibrium, what we did on day 9. However, try to do it using the principle of virtual work, and you should end up with the same answer. If you have any questions, be sure to bring them to class, and I will see you then.